Hello, welcome back. In the previous lesson we derived the Lorentz transformation equations. They show that time and position, as measured in the reference frame S, can be related with time and position as measured in a reference frame A'. Those equations show that both of these measurements in S depend on both of the measurements in S'. But let's stop for a moment to think about what this all means. First of all, what do we mean by a measurement? When we measure, we are comparing something to a handle in our measurement device, be it a ruler or be it a clock. When we measure a distance, a position, we are looking at that mark in our ruler. What mark coincides with that specific point? Let's call it event. Let's think about point events that happen in space and time. A measurement in time is the position that the hands of my watch are indicating when that event just happened. But we must be very careful here on how we define measurement and how we define observe, or how we define see or watch. The equations we derive Lorentz transformations refer to the times and positions in both reference frames as measured in the specific positions where those events take place. Consider you are the observer at the origin of your inertial frame with your perfect watch. If an event takes place right at the origin where you are, then whatever indicates your watch, that is the time measurement corresponding to that event from your reference frame. But what if what happens takes place at a distance like 1 light second from you? Light needs time to travel to your eye and your watch. So, will your watch register a different time for that event? Well, let me introduce a huge grid of rulers and clocks. We have 3 dimensions of space, x, y, and z. So we set infinite long rulers in all 3 directions. Consider that in each direction we place one infinitely long ruler every meter. This way we build an infinite 3-dimensional grid of rulers that we will use to measure positions of events. We have kind of infinite boxes of 1 meter by 1 meter by 1 meter. In each one of those intersections we place a clock. Infinite clocks, all of them synchronized in that reference frame. Everything is at rest, that is your reference frame. So 1 meter is 1 meter everywhere and 1 second is 1 second everywhere. Now, let's define what a measurement is in our inertial frame. When an event takes place, imagine a small explosion somewhere in space and time. There would be one of those intersections of our grid right very near where that explosion took place. The coordinates of that intersection will be the measurements of position, and the time of that clock will be the time coordinate of that event. Because light needs 3 nanoseconds to travel 1 meter, we have a resolution of 3 nanoseconds and 1 meter. If you want more resolution, you can always put more rulers. Your rulers space 33 centimeters, and you will have a resolution of 1 nanosecond and 33 centimeters, and so on. So the time that the Lorentz equations tell us is the time in that reference frame, assuming we have a perfect grid of rulers and watches. That is what we mean by measurement. Of course, if you are far from the event, good for you if it's an explosion, then you will see that event a bit later. For example, Betelgeuse is a super red giant star in the constellation of Orion, about 600 light years from us. It is in the last stages of its life, so when it explodes, light will need 600 years to reach Earth for us to know that it died. Remember that nothing can travel faster than light. Maybe it already exploded 50 years ago. We will talk about this other effect later in this course. Now, let me consider the following example. Imagine there is a train traveling at speed v in the x direction, as always. Remember that we will always use, for simplicity, that the moving frame moves to the right on the x-axis. And that for t equals to t prime equals to 0, then x is equals to x prime equals to 0. In a wagon on the train, there are 3 clocks synchronized in the moving reference frame. The length of the wagon is L. We set our origin of the moving inertial frame to be right at the center of the wagon. I want to calculate what will those clocks read from my reference frame when the origins of both reference frames coincide. So the train is moving to the right when the origin of that moving reference frame is on top of my origin of my reference frame. I want to know what the other clocks are reading right at that time as seen from my reference frame. So here we have our wagon, our train that measures a length of L0. I will put the subindex 0 to make reference to everything that is measured in the reference frame, in the proper reference frame. So people in the train measure that this length is L sub 0. So that's what we call the rest length, as measured by someone that is at rest with respect to that train. These are the Lorentz equations that we found in the previous lesson for the position x, for the position time, and these are the initial core conditions that we have. Remember, we turn the clocks on right when both origins coincide. And we have 3 clocks. One is clock 1, clock 2, clock 3. Clock 2 is right at the origin of that moving reference frame. Clock 1 is L0 over 2 distance, and clock 3 is negative L0 over 2. So in order to find the new coordinates, I want to find, first of all, I will write the coordinates in the moving reference frame, which is x1 prime is going to be L sub 0 over 2. That's the coordinate of this clock as measured from the train. x2 prime is 0, it's right at the origin, and x3 prime is negative L0 over 2. That is the position of that third clock. Now, in the moving reference frame, the events we're going to measure is right when time is equals to 0, and all 3 clocks indicate 0. So t1 prime is 0, t2 prime is 0, and t prime 3 is 0. They are synchronized on the moving train, and right at that instant of time, all of them indicate 0. So let's calculate x1, x2, x3, t1, t2, t3 in the reference frame of this station. Let's say that x1 is going to be that thing there, so gamma times x1 prime plus v t1 prime. X1 prime is that thing there, t1 prime is 0, so this is going to be gamma L0 over 2. x2 is going to be the same, gamma x2 prime plus v t2 prime, and that is x not prime is 0, t prime 2 is 0, so this is 0, as we already knew, of course, and x3 is gamma x3 prime plus v t3 prime, which is t3 prime is 0, x3 prime is that, so that's negative gamma L sub 0 over 2. Those are the coordinates in our reference frame. We have t1 is going to be that expression there, gamma multiplied by t1 prime plus v x1 prime divided by c squared. Time is 0, x1 is that thing there, so let me substitute. That is gamma velocity x1 prime, which is L0 divided by 2 c squared. T2, we know that is going to be 0. T2 is 0. Just use that, and remember that t prime 2 x prime 2 is 0. And now t3 prime is that gamma t3 prime, that's without a prime, v x prime 3 over z squared. We substitute, we have that is going to be 0 again, and remember that x prime 3 is negative, so that is negative gamma v z naught over 2 c squared. So those are the times. Look, that this is a positive time, is ahead in time, that's a negative time, is retarded in time. So we see that all 3 clocks are not synchronized, and we know that this one is a bit ahead, that's a bit retarded, and that's the only one that coincides with our reference frame. Let's put some numbers here. Let's assume that the length is 10 meters and that beta is 0.5, or so the train is traveling at half the speed of light. First, let's calculate what is gamma. This gamma, remember, 1 over the square root of 1 minus beta squared. For a beta of 0.5, gamma is 1.15. If we substitute those numbers into these expressions of time, we find that T1 is 9.6 nanoseconds and T3 is negative 9.6 nanoseconds. That's what those clocks indicate. Use C as 3 times 10 to the power of 8 meters per second. So those are the times that we would read on those clocks. And remember, we will read in the sense of that infinite grid of rulers and clocks that we have. So as if we had our eyes right there where those events take place. So light doesn't spend any time reaching our measurement devices. We have a measurement device here, another there, and another there. We have infinite measurement devices there.